In this video, we're going to introduce a concept that is known as the buffer solution. So in some previous videos, I have talked a little bit about why understanding acids and bases and understanding pH is important. Both that acids and bases are just kind of everywhere. It's a really common type of substance and type of reaction in chemical systems, biological systems, and just in the world at large. And also that certain chemical and biological systems only function properly within a fairly narrow pH range. And outside of that pH range, your reactions don't work as well or at all, and biological structures can start to break down. So buffer solutions are the main way that we can keep a chemical or biological system within the pH range where it wants to be. So buffer solutions exist in all sorts of natural systems that are specifically designed to keep them at the pH where they function properly. So all of the cells in your body are basically little sacks of buffer solutions that keep the pH where they need to be. Your bloodstream is buffered. Most of the foods that we eat are acidic or basic. So if your blood wasn't buffered, most of the things that you eat would cause a big pH change in your bloodstream, and that would be really problematic. But because your blood is buffered, it doesn't really matter what you eat, the pH actually stays quite constant. A buffer solution is just something that resists pH change, where the pH stays stable when some acid or base is added. So the way that buffer systems work is that they contain a mixture of a weak acid and its conjugate base. And when you add a little bit of acid or a little bit of base to that system, the pH stays relatively constant, which I'm going to demonstrate now.
So I'm going to demonstrate what I mean by a buffer being able to resist pH change. So what I have here are two different samples. I have pure water here, and I have a sample of a buffer solution here. So I've added a pH indicator to both of these solutions, known as universal indicator, which is actually a mixture of multiple different pH indicators that is designed such that it pretty much continually shifts its color throughout a pH range from about 4 to 10. And it goes in rainbow order, starting with red at about pH 4 and going up to purple at around pH 10 or so. So judging by the color, you can tell your pH pretty accurately using universal indicator. So both of our samples here are starting out green, which indicates that they're right around pH 7. So I chose a buffer that would be starting out at the same pH as water for demonstration purposes. So water is just water. It is not a buffered solution. So if I add just a little bit of acid or base, we will see the pH change drastically, and that will be reflected in the color. So right now we're right about pH 7 since our color is green. So I'm going to add just a single drop of a hydrochloric acid solution. This is 0.5 molar hydrochloric acid. I have to speed up the process here a little bit. And you can already see the color starting to change. So after just, that was about 4 or 5 drops in total, wait for it, about 5 drops has changed our color from green to a much more yellowish color. If I add just a little bit more, a few more drops here, that was probably about a milliliter or so in total, we can see that we are well on our way to red. So just about 1 milliliter of this solution, which is a pretty small amount, has brought our pH from 7 down to, I would say this is about 4.5 or so. It's kind of a red-orange, not a pure red. So if we add a similar amount of acid to our buffer solution, So we're once again starting at pH 7. If I add that same quantity of about a milliliter, I'm just going to add it all at once here, to my buffer solution, nothing has really changed. Our pH is still the same, our color is still the same, our pH is still right about at 7. If we were able to measure it really precisely, we would see a very, very small decrease in our pH, but we can see that the buffer solution is resisting pH change, that I'm adding acid to it and the pH is staying pretty much stable, that I have to add quite a lot of buffer solution. Let's try and keep track of it. So a second milliliter has done pretty much nothing. There's 4, 5, and maybe we're starting to see a shift towards yellow here. So this is probably pH 6.5 or so. So 5 times as much acid added to my buffer solution has changed the pH by like half a unit, instead of that 1 milliliter changing it by almost 3 whole pH units. So the pH of our buffer solution changes much more slowly. And the same goes for addition of base, that if I add small amounts of a base solution, so I have 0.5 molar sodium hydroxide here, I'll add about 1 milliliter, and we can see that our pH is changing pretty drastically. It's taking a while to mix everything together, but we've actually gone all the way to purple, so it looks like I added a little bit more of this solution, that our pH has shifted all the way from around 4 or 5 up to about 10 just by adding that 1 milliliter of sodium hydroxide. And by contrast, if I add the base into our buffer solution, that's probably about 2 milliliters or so. That was a big squeeze. We see a whole lot of nothing. We see very little change. So this is really important for any biological or chemical systems that are really sensitive to pH changes. They buffer themselves, or can be buffered by an experimenter in order to help maintain a constant pH.
So in order to function properly, our buffer solution must contain a weak, that's important, conjugate acid-base pair. So a weak acid and its conjugate base, or a weak base and its conjugate acid, however you prefer to think about it. And they must be present in roughly equal quantities. Doesn't have to be exact. Up to about a 1-to-10 ratio in either direction is fine, but approximately equal-ish. So the way that this works, we know that the conjugate base of a weak acid is a weak base. So by having the conjugate pair in solution together, you have both a weak acid and a weak base already present in your solution. So the weak acid in your solution, which we're going to represent as HA for just generic acid, reacts with any added base. So if we think about what the net ionic equation for that would look like, if we're adding strong base into this, hydroxide is going to be our actual reacting base that's involved, along with our acid. So the hydroxide is going to pull the acidic hydrogen off of our acid, leaving us with the conjugate base of that acid and water. So note that we are not producing either hydronium or hydroxide in this reaction, which means our pH doesn't really change very much. The pH of a solution is controlled by the hydronium and hydroxide ratio, really, by the hydronium concentration. So if we're not changing the amounts of those things that are present in our buffer solution, our pH isn't changing. As we add in base, it gets immediately reacted away by the acid that's present in the solution, and the pH is able to stay relatively constant. Same idea if you're adding acid into your buffer solution. The weak base that is present in the buffer solution, the conjugate base of our weak acid, so we'll represent that as A-, it's just the anion from our weak acid, is there to react with any added acid. So our weak base, if we're adding a strong acid in, which is usually what we're thinking about here, that would be represented as H3O plus in a net ionic equation. So that strong acid, that hydronium ion, will donate H plus to our conjugate base, creating HA, or acid. And when hydronium loses a proton, it becomes water. So once again, same idea, we're not producing any hydronium or hydroxide in this reaction. We're adding some hydroxide in and it's immediately getting reacted away. This reaction goes to completion. So once again, our pH doesn't really change. Essentially, you add base, there's acid there to absorb it. You add acid, there's base there to absorb it. And all you're really doing is converting acid to conjugate base or converting base to conjugate acid, but you're not really affecting the hydronium and hydroxide concentrations significantly. So your pH does change very slightly when you add, when acid or base is added. But it takes a lot, as you saw in the demonstration, to cause a really significant pH change. So depending upon like how narrow your window is where your system functions the way you want it to, you do want to be careful that there's not too much acid or base being added, because everything does have a limit that we can see based on these reactions, that if you, let's say, just keep adding base and keep adding base and keep adding base, at some point you're going to run out of acid for it to react with. There's only so much acid in that solution. And that is known as the buffer capacity, and we can exceed that. So the buffer capacity is essentially how much acid or base a buffer can neutralize before significant pH change occurs. And what significant means is going to vary depending upon your needs. Usually you would want to consider the buffer capacity before your pH goes outside of the range where you want to keep it. So buffer capacity is a very loosely defined sort of term, but the point is that there is a limit to how much a buffer can absorb before the pH starts to change. So if too much acid or base is added, the pH will start to change quickly because you've consumed all of the acid or base that is there in the solution. So the pH of your buffer solution is controlled by the ratio of weak acid to weak base, as well as the strength of the acid. So if you are creating a buffered system like I did for the demonstration that I just showed you, and you want it to be a particular pH, you want to choose an appropriate acid, and you need to kind of fine tune your ratio as well. And we can use an equation known as the Henderson-Hasselbalch equation. It's wrong. There we go. To calculate the pH of our buffer solution, if we know everything else about it, or we can use it to figure out how much acid or base do we need to put in to get a particular pH, but we'll mostly just be using it to calculate pH at this point. So the Henderson-Hasselbalch equation says that the pH of a buffer solution is equal to the pKa of the acid plus the log of the base concentration over the acid concentration. So the one thing that is a little bit unfamiliar here is the pKa is not something we have specifically talked about, but remember that P means take the negative log of that thing. So the pKa is just the negative log of the Ka, of the acid dissociation constant. So if we want to calculate the pH of a particular buffer solution, all we need to know is the concentration of the acid, the concentration of the conjugate base, as well as the Ka for the acid, so that we can find the pKa. So for example, let's say a solution is created that contains 0.5 molar acetic acid, which has a Ka of 1.8 times 10 to the minus fifth, and 1 molar sodium acetate. We can calculate the pH of this solution. First. So we'll use the Henderson-Hasselbalch equation. So we'll be using this guy here. If you're asked to calculate the pH of some solution, you always want to kind of assess what it is. We've talked about how you calculate the pH of a solution containing just a strong acid or just a weak acid, or just a strong base or just a weak base. What you need to recognize here is that you have a weak acid and you have a weak base. So you have a weak acid and you have its conjugate base. And what that means is that you have a buffer solution here. So that's the first thing you need to recognize in a grander context of chemistry outside of just this lesson, is that this is a buffer, is the first thing you need to notice in your brain. And that means that we're going to use the Henderson-Hasselbalch equation. We only use that equation for buffers. So our Henderson-Hasselbalch equation, pH is equal to pKa plus the log of our base concentration, which is the acetate ion, over the acid concentration, which is the acetic acid. So our base and acid concentrations are given to us directly. So our acetate was 1 molar. Each unit of sodium acetate produces 1 acetate ion. So if we have 1 molar sodium acetate, we have 1 molar acetate as well. And our acid concentration was given to us as 0.5 molar. So the only other thing we need here is the pKa, which we are not given directly, but we are given the Ka. So the pKa is just the negative log of the Ka, which is 1.8 times 10 to the negative fifth, which comes out to about 4.74. So that is the last piece of information that we needed to be able to plug in to our formula here. So our pKa is 4.74 plus the log of 0.5, nope, 1 was on top, sorry. 0.5 was on the bottom, which gets us a pH of about 5.04. So that was what we were looking for, was to calculate the pH of the solution. Since it's a buffer solution, the Henderson-Hasselbalch is the easiest way to do it. You can do it via an ice table and typical equilibrium calculations, but the Henderson-Hasselbalch is kind of a shortcut and is much easier. So the other things you want to be able to think about for this type of system are what's happening when acid or base is added. So if I took this buffer system and I added strong acid to it, what's the reaction that's happening? If I added strong base to it, what's the reaction that's happening? So we talked about that, generally speaking, up here with these two reactions. All we're doing is plugging in a specific weak acid and a specific weak base that apply to this system. So we can write the reaction that happens when a strong acid is added to this solution. And write the reaction that happens when a strong base is added to this solution. So why don't you take a moment, pause here, and try to write these two reactions on your own. So when we're adding a strong acid into our buffer solution, this is going to be represented as H3O plus. Strong acid is going to react with the base in my solution. So the base in this solution was the acetate ion. So I will want to have the acetate ion reacting with the strong acid, the hydronium, and then it's just a proton transfer that happens. So my hydronium gives a proton to the acetate ion, which turns it into acetic acid. And when hydronium loses that proton, it becomes water. On the other side of things, writing the reaction that happens when a strong base, which we'll represent as hydroxide, is added to this solution. Any added base is going to react with an acid. Bases always react with acids and vice versa. So the acid in this system was the acetic acid that will react with the hydroxide that's being added. Hydroxide will pull off the acidic proton from the acetic acid, leaving us with the acetate ion. And when hydroxide gains that proton, it becomes water.